This video describes a method of approximating pi. Pi is the ratio of the circumference of a circle to its diameter, or twice its radius. Approximations to the circumference can therefore be used to calculate approximations to pi. For instance, we could approximate the circumference of a circle with the perimeter of an inscribed square. Divided by 2r would give us an approximation to pi. An even better approximation to the circumference of the circle would be the perimeter of an inscribed regular octagon. Again, that perimeter divided by 2r would give us an approximation to pi. The approximations could be improved by using an inscribed regular 16-sided polygon and its perimeter divided by 2r would give an even better approximation to pi. It could be shown that as the number of sides of the inscribed regular polygon increases, the perimeter of the polygon approaches the perimeter or the circumference of the circle. And so, as the number of sides of the inscribed polygon increases, so our approximation using that perimeter provides a better approximation to pi. Although we can't calculate the limit of n s sub n over 2r as n goes to infinity directly, we can get approximations to pi to arbitrary accuracy by using large values of n. That is, calculating the side length of an n-sided regular inscribed polygon will allow us to calculate pi to arbitrary accuracy. We can calculate s sub n for large values of n by using a recursive formula which provides s sub 2n in terms of s and n and r. With no loss in generality, we can derive the recursive formula using an inscribed square and an inscribed octagon, as shown. In the diagram, we'll consider the octagon as having side length s sub 2n. Clearly segment AD would have that length. And segment AB would be a side of the square, and so its length would be s sub n, the side length of a four-sided inscribed polygon. It can be shown that AC is half the length of AB, and so AC would have length s sub n over 2. Note also in the diagram that segments OA and OD each have length equal to the radius. As all angles formed at C are right angles, we can write an expression for the length of segment AD using the Pythagorean theorem. Substituting in s sub 2n for AD and s sub n over 2 for the length of AC, we can rewrite this expression as it's shown in the upper right. Segment CD can be expressed in terms of segments OD and OC using segment addition. And finally, the length of segment OC can be written in terms of the lengths of segment OA and AC using Pythagorean theorem. Again, note all angles at C are right. We can rewrite this equation, putting in R for OA and S of n over 2 for AC. Considering the three equations at right, we could substitute in the right-hand side of the second equation for CD in the first equation, and then we can substitute the right-hand side of the equation for the segment length of OC in for the segment length of OC in this result, and we're left with an equation all in R and S of n for S of 2n. To calculate S of 2n for large values of n, we would use this formula repeatedly. For instance, calculating the side length of an octagon, putting that into this equation as S of n to get the side length of a 16-sided inscribed polygon, and then allowing that result for S of n back into this formula to calculate the side length of a 32-sided regular inscribed polygon. And so we would quickly increase the number of sides of our polygon, whose perimeter we use to approximate the circumference, and so our approximation to the circumference gets better, and our use of that in our approximation for pi gets better. I hope this was informative.